Hello students, today we will discuss about various thermal methods of analysis. As the name indicates, thermal methods means the methods which involve temperature. We will study the effect of temperature on some physical property of compounds. In the lecture, we will talk about introduction, different techniques of thermal methods, and out of several methods we will discuss about TGA, that is thermogravimetry analysis, DTA, differential thermal analysis. We will talk about types of TGA curves, factors that affect TGA curves, and their applications. Thermal analysis is the part of material science in which the properties of materials are studied as they change with temperature or time. These techniques are those in which a physical property of a substance or its reaction product is measured as a function of temperature. More than a dozen thermal analysis techniques have been developed like TGA, DTA, DSC, TMA, etc., which are used in determining the physical properties of the given system as a function of temperature. We will discuss little bit about the different techniques which are very well known. For example, the first one is thermogravimetry. It is represented as TG and sometimes as DTG, that is differential thermogravimetry. In this technique, we study change in weight of the sample with change in temperature. Second one, differential thermal analysis, commonly abbreviated as DTA, in which we measure difference in temperature between the sample and a thermally inert reference material, both heated identically, which means we will heat our substance as well as we will heat an inert reference which has no effect on temperature, and then we will monitor difference in temperature. Next is differential scanning calorimetry, known as DSC, in which rate of change in enthalpy is measured as a function of temperature. Next one is evolved gas analysis, commonly known as EGA, in which we study nature of gases evolved. Then thermodilatrometry, in which change in the dimension of the sample under zero load is measured as a function of temperature. Then we have dynamic mechanical analysis, which is abbreviated as DMA, in which change in viscoelastic properties under oscillatory load is measured. Thermo-optometry, commonly abbreviated as TOA, in which change in optical property is studied as a function of temperature. Then thermomagnetometry, it is written as such, there is no common abbreviation for this technique, in which change in magnetic property of a substance is measured as a function of temperature. Today, we will talk about the first one, that is thermogravimetric analysis, commonly abbreviated as TGA. In thermogravimetric analysis, the mass of a sample in a controlled atmosphere is recorded continuously as a function of temperature or time. Then a plot of mass or mass percentage as a function of time is prepared, which is called as thermogram or a thermal decomposition curve. This is a common instrument for TGA analysis, in which you can see we have a microbalance, then we have a thermocouple here, then we have a crucible in which we kept our compound, and then we have a furnace here. Now, if we represent it, a systematic representation can be something like this, in which we have a furnace right here, which is temperature programmable furnace. Then we have a sample holder here, and a recorder is connected to the temperature sensor through a balance control. And here we have a recording balance. So, we have a recording balance, balance control, and a simple recorder. If we look at the parts of the instrument, we require a microbalance, a sample holder, or sometimes we call it as crucible, a furnace which may be a heater, boiler or oven type, a system to measure temperature. Then to control the heating rate, we require some device, and finally a data recording unit which measures the change in weight with respect to temperature. Let us come to them one by one. The first one is microbalance. There are many thermobalances available which range in mass from less than 1 milligram to 100 gram. The usual range of thermobalance in thermal analysis is preferred between 1 milligram to 100 milligram. The sample holder is kept in the furnace, which interposes a light shutter between a lamp and one of the two photodiodes. A change in mass causes a deflection of the beam, and the resulting imbalance in the photodiode current is amplified and transformed into mass loss. There are two types of balances used in the instrument. First, deflection type, and second, null type. Let us see what is deflection type balance. There are different types of microbalances like beam, spring, cantilever and torsion balances. In beam type of balance, the conversion of deflected beams takes place into the weight change. Say for example, this is the initial weight. You can see the balance is horizontal, and when there is a change in the mass, this causes a deflection, which is due to the conversion of deflected beams, and we can immediately notice that there is a change in weight. In cantilever beam, one end of the beam is fixed. You can see here one end of the beam is fixed and the second end is free, where we keep our compound. Now, it undergoes deflection, which can be recorded with the help of photographic trace. So, when we keep our substance or compound in the initial stage, this balance is horizontal, and when there is a change in mass, we can see that this cantilever type of balance shows a deflection. In helical type of balances, elongation or contraction of spring occurs with change in weight, which is recorded with the help of transducers. You can see here, this is a spring balance. We keep our sample here, and when there is a change in mass or change in weight, this spring shows a deflection which may be elongation or contraction, and it is recorded by the balance. In the torsion wire balances, the beam is attached to hard torsion wire which acts as fulcrum, and the wire is attached to one or both ends of balance to make the deflection of beam proportional to the weight changes. This is the example. You can see here we have a torsion wire and it shows deflection whenever there is a change in weight. Null point balances, which consists of a sensor which detects the deviation from the null point and restores the balance to its null point by means of a restoring force. So, this is an example. Here you can see the restoring force keeps the balance in the straight or horizontal form. Then comes the second part, sample holder. The sample is placed in a sample holder or a crucible. It is attached to the weighing arm of the microbalance, and a variety of crucibles of different shapes and size can be used in the instrument. Crucibles are made up of platinum, aluminum, quartz or alumina, etc. This is an example where you can see that we have variety of crucibles or number of crucibles we can put in the instrument. Shallow pens. These are used for volatile substances in which the rate controlling step is diffusion. Sometimes we use deep crucibles which are used in such cases where side reactions are required, such as in industrial scale calcinations, etc. Loosely covered crucibles are used in self-generated atmospheric studies. Sometimes we require retort cups which are used in boiling point studies. Then comes the furnace. For TGA, furnaces usually cover the range from ambient temperature, which is usually 25 degrees to about 1000 degree Celsius. Although some have temperature up to 1600 degrees Celsius, but the common ones are the one which are having range from ambient temperature to 1000 degree Celsius. Heating rate can often be selected anywhere from 0.1 degree Celsius per minute to 100 degrees Celsius per minute. Nevertheless, we must realize that if heating rate is lower, the results are more accurate. This is an example of common furnace which is used in instruments. Nitrogen or argon gas is usually used to purge the furnace and prevent oxidation of the substance. Here we are showing you position of furnace with respect to balance. You can see here in case A, this is our furnace and the balance is on the other side. In case B, you can see they are vertically opposite. The furnace is on left, but on the top, and balance is on the bottom side. In the case C, we can see that balance is on the same horizontal axis, whereas balance is on the right hand corner. Then comes the temperature measurement. The most common method is use of a thermocouple, which is an electrical device consisting of two different conductors forming electrical junctions at different temperatures. Chromyl or alumyl thermocouple is an alloy of platinum and rhodium and can be used easily up to a temperature of 1100 degree Celsius. For still higher temperature, tungsten or rhenium thermocouples can be used. Heating rate is the rate of temperature increase which is normally recorded in degrees per minute on the Celsius or Kelvin scales. The heating or cooling rate is said to be constant when the temperature time curve is linear. Here we are showing you the effect of heating rate on decomposition temperature of polystyrene. You can see here on the x axis we are plotting temperature in degrees Celsius, whereas on the y axis we are showing weight percentage. Here you can see that in the beginning up to about 350 degree there is no change in weight. Whatever weight we are taking, it is 100% of the same weight. But then with increase in temperature, there is a loss in weight and we comes to about 0% weight. And these curves A, B, C and D, they represents the different temperatures by which we are causing the rise in temperature. In case A, it is 20 degrees Celsius per minute. In case B, it is 10 degrees Celsius per minute. In case C, it is 5 degrees Celsius per minute, and the curve D 1 degree Celsius per minute, which means that if we cause heating at a very fast rate, we get results which are not very accurate, and therefore, we must use a reasonable heating rate to get the best results. The data recording units are of two types. First, time based potentiometric strip chart recorder, which are very common, and second, XY recorder. The advantage is to check the heating rate of the furnace for linearity. XY recorder can provide curves having plot of weight directly against temperature. Now, there are various types of TGA curves which have been classified according to their shapes. For example, case 1, here you can see it is practically horizontally linear, which means there is no change in the weight. Second, here you can see there is almost exponential decay, and which means that the sample is showing desorption or drying nature. The third one, here you can see that initially it is constant, followed by a decrease and then again constant, which shows single stage decomposition of the substance. In the case 4th, we can see here that it is horizontal followed by decrease, and we see here several such steps which shows a multi-stage decomposition. Then comes 5. Here we can see that there is no clear step. Initially it was constant and then it is decreasing very fast with no clear steps, which means that it is showing no intermediate or heating rate is too fast. Then here we can see in the next case, initially it was constant, then it increases and then again becomes constant, which means there is some atmospheric reaction is taking place. Finally, the seventh type, here you can see a curve which shows increase followed by a decrease, which shows that the product decomposes at higher temperature. Let us consider an example of calcium oxalate. Here on x axis we are increasing temperature from 0 to about 1000 degree. Now you can see here that here initially the weight was 100% and in the first step it decreases and then remain constant up to about 400 degree, and in this step there is a weight loss of about 0.8753 milligrams, that is the weight now becomes 87% and it shows the loss of water which is 12.57%. In the second step again we see that there is a loss in weight percent, and here the loss is 1.355 milligram, which indicates the loss of 19.47% carbon monoxide. In the third step we see the loss of about 30.07%, which is due to carbon dioxide, and you can see here the temperature is about 600 degree and the loss in weight is 2.093 milligrams. That means if we heat calcium oxalate up to about 200 degree, it loses water. If we heat it up to about 400 degree, it loses carbon monoxide, and if we heat it up to about 600 degree, it loses carbon dioxide. Now here the same curve, we can see here the mass change 12.28%, 18.06% and mass change 29.22%. The residual mass finally remains 39.75% at 999.5 degree Celsius. Now let us consider the analysis of this curve. The first step is that we were taking calcium oxalate monohydrate, and in the first step we loses water and we get anhydrous calcium oxalate. In the second step, the calcium oxalate loses carbon monoxide at about 400 degrees Celsius and we get calcium carbonate. And in the third step, the calcium carbonate at about 600 degree loses carbon dioxide and we get calcium oxide as the final product. Let us now consider factors that affect TGA curves. The first one is instrumental factor. The heating rate, as I told you that if heating rate is too fast, you may not get a stepwise loss in weight. The furnace atmosphere, sample holder and the sample characteristics, which means sample mass, particle size of the sample, effect of heat reaction, compactness of sample and purity and thermal stability also affect TGA, like solid state reaction, decomposition of organic and inorganic compounds, we can easily apply TGA, determining composition of various materials, corrosion of metals in various atmospheric conditions, pyrolysis of coal, petroleum and wood can be easily studied by TGA, roasting and calcination of minerals, evolution of gravimetric precipitates, oxidative and reductive stability. To summarize, today we learned about different techniques of thermal methods, and out of several techniques, today we discussed in a little bit more detail about TGA, which is thermogravimetric analysis. In this technique, we have discussed the type of various balances which are used, the different nature of curves which we get during the analysis, and we have also discussed the various factors which affect TGA curves, and how we can use TGA for the analysis of various materials and its industrial applications. In the next lecture, we will talk about DTA, which is differential thermal analysis, which is also very similar to TGA and deals with change in weight percentage with respect to time or temperature, but since we are taking the difference in place of normal steps, we get peaks which are very sharp in nature, and we will deal with them in a little bit more detail in my next lecture.